Okay, so we'll get started. So the focus for today's discussion would be stability. But before that, I wanted to talk about the input-output system as well. So far we were talking about x dot equals to a of x, and we were trying to characterize the solutions for that. Now I'm looking at x dot of t equals to axt plus but, and my y of t is equal to cxt plus but, and ABCD matrices are of appropriate dimension so that this equation makes sense. Anyone remembers what the solution to this is? X of t naught is equal to x0. So the solution to this is given by t naught to t so that's for the state equation, and then the observation is c multiplied by the same thing plus dut. We talked about it several times so far. Phi is of course the state transition matrix, and now we know how to compute this. This is not just with t naught, with tau. It's exponential of a t minus tau. This is called the state response. And this would be input-output response. Okay, so one thing that we should keep in mind if you're taking this class and you're working in the area of control systems, almost always for every system that you would ever interact with, you would actually see only the input-output response. That's the only thing you see. So you give it an input, what you observe is the output. The state response is actually extremely difficult to get. Can someone tell me why the state response is difficult to get? So I think it's the fact that this is the observation, this is what you are measuring from your sensors, and this is the input. I think it's easy to understand that you have an input-output response. But I want you to think a little bit and tell me, how do you know what the state response of the system is going to look like? What do you have to do? Yeah.
would have to know, I guess technically you can set your initial conditions, but you would have to both know your initial conditions and have a perfect model of what the system will do over
Right.
time.
So you need to have the perfect model for this whole thing, right? Do we always have the perfect model? We generally don't. In fact, when you turn on the air conditioning system in your vehicle, I know that most of you are car people, so I can use the vehicle example. So if you turn on the air conditioning system in the car, there's a lot of dynamics that is happening. There is refrigerant flowing into certain compressor. The compressor is compressing something, then it's going through some heat exchanger and so on and so forth. So a lot of fluid mechanics happening, a lot of heat thermodynamics equations are working out. But you know what you actually feel inside the cabin is that the temperature of the cabin is going down or going up depending on what the situation is. And the input that you have given, which is I want the set point of the particular uh, of my cabin to be 72 degrees Fahrenheit, 78 degrees Fahrenheit, whatever is your favorite temperature, right? So you give it an input, you're observing the output, and you don't quite know what's happening within the system. Okay, so that's something that is so this is something that you need to keep in mind. And so how do we get to this whole thing? How do we get to this entire equation? Well, somebody like you spent their entire PhD trying to model the system. Okay, so somebody models the thermodynamics part, somebody models the fluid mechanics part, somebody models the temperature heat exchanger part, and then you combine all of these 3 or 4 different models in order to get the complete description of the system. Okay, and so for most of the systems we don't quite have the complete description, we only have the partial description of the system. Sometimes that partial description is good enough to design the control strategy, and sometimes it is not. So in healthcare you don't quite have the complete description of the system. A lot of people are working on a lot of different things in order to get a better description of the system in order to design better control strategies. But in the case of automotive systems, I think people know a lot about individual components and the model for the individual components. And so now I think a lot of people are trying to figure out how to merge all of these different components together in order to do better control and better, say, energy management, better safety, better diagnostics, and so on and so forth. So with that, I want to mention 2 terms: external description. This is the input output description of the system. There is an internal description, which is the input state output description. So in external description, you know UT and you know YT, and in the internal description, you know XT as well. Okay, so state is also known. And I want to emphasize again, getting an internal description of the system is a very, very difficult affair. On the other hand, getting the external description, at least to get some model of the external description, is comparatively much easier. So we talked about, for the internal description case, we talked about the impulse response. So we'll do that for the external description now. So if you recall, YT is this particular expression, integral of T naught. Okay, let me write it better. Maybe I'll erase this side. So impulse response in the external case. My x naught equals to 0 and my u naught, my u t equals to delta, let's say tau or t minus tau. Infinity t equals tau, 0 t naught equals to tau. Remember that the way we had conceptualized the delta function, area under the curve equals to 1. So if you plot the delta function, the area under the delta function is going to be equal to 1. That's how we conceptualize this function. It's not a real function, but that's how we are conceptualizing it. So I need to find what yt looks like. So can someone tell me what is the yt for this case? So x naught is equal to 0. So I can just substitute this equal to 0. Then I have this integral term and then I have this dut term. Oh, and I have to multiply this by matrix C. So I have integral t naught to t C b delta t minus tau d tau plus d ut, and this one is equal to 0 for t not equal to tau. Oh, I think I made a mistake. I need to use some other number here. Let me make it t0 because tau is already used. I'm going to put the impulse at time t equals to t naught. T equals to t naught. Okay, so the book doesn't specify at what point t naught they have given the impulse, but I presume this should be t naught. If I am doing the impulse at t naught, and this should be delta t minus, tau minus t naught. Mu tau is delta tau minus t naught, yeah. Okay, so perhaps no, I think they have used u tau, that's okay, perfect. So this term is going to be 0 if t is not equal to t naught, and this is my u of tau. So I'm going to write this overall as integral t naught to t C phi t tau b plus d delta t minus tau u tau d tau. Okay, so this expression gives me the impulse response for the output. So I don't have the state response because I cannot measure the state. I can only measure the output. I can only measure the temperature of the cabin, but I can't measure what the pressure inside the compressor is. I can't measure what the heat exchanger is trying to do, how much heat is coming out of the heat exchanger, and all of that complicated stuff. The only thing I have is a temperature measurement of the cabin. And so this is the transfer function. I mean, not the transfer function, but the impulse response given the input. This is the impulse that you are seeing, the impulse response that you are seeing at the measurement level. Remember, this is yt, not xt. So this differs from your 3551 or equivalent class, feedback controls class that you might have taken, because in many of those classes, we assume that you can observe the entire state of the system. You have a single input, single output problem, and you can observe the output directly. But now when we are talking about input-output system, where you probably may not have the state response or the state equation of the system, all you are observing given the input is what you are seeing at the output level. So that defines the impulse response of the output, and this one is, it's equal to this for t greater than tau. It's equal to this for t greater than equal to tau, and it's 0 for t less than tau. So, and this one is called the impulse response matrix. So, whenever you are exposed to a new dynamical system, what you will observe is this impulse response, and hopefully you will have enough training in thermodynamics and electrical machines and whatnot to be able to figure out what this equation and this equation looks like. Okay. Any questions so far on this topic? It's all straightforward math. The other thing that I wanted to cover is if you wanted to change the state, remember we talked about the fact that you can have a transformation of the state, invertible transformation of the state. How does the input-output expression change? So that's something I'm just going to write on the board. We did the derivation for a simple case yesterday, not yesterday, day before. And so you need to know what happens in the input-output case if you were to change the description of what you are measuring and what your state looks like. So I'm going to assume my x tilde of t equals to p x of t. One thing I want to specify here, p is not a function of time, only x is a function of time. And in this case, your xt p inverse x tilde of t, and based on this, you can write it as x tilde dot of t equals to PAP inverse x tilde t plus PBU. Perfect. And in this case, your impulse response is equal to the impulse response in the other case. In other words, by renaming the state, you don't quite change the impulse response of the system. Yes, please.
I was kind of curious. So if you had a linear system that you're going to identify, would you use an impulse response? Because it seems like you would have your derivative terms would be infinite, right? So wouldn't that like not be useful to classify a physical system? Or I'm not sure if there's something I missed about that.
So what happens generally speaking is whenever you have a continuous control action, what you view it, so mathematically the way to think of it is as a sequence of impulses. Okay, so if you know the impulse response of the system, you can reconstruct the response of the entire system for any given input command. Okay, so that's why people tend to study impulse response, because that's the basic unit of a system that you can then compose in different manners in order to figure out what the response of the system looks like for different inputs. What I'm trying to cover here is the fact that just because you change the description of the state of the system doesn't mean that your impulse response will change. Your impulse response still remains the same. Remember that the input is the same, it's the input whatever you are giving it, and the output that you are measuring is the same. You're not really changing the output. All you're changing is the internal description of what the state is. So if you're having a temperature as your state, you can say, look, I'm not going to talk about temperature as the state, I'm going to look at the resistor, and the resistance of that particular resistor is the state of the system. And that's completely fine. All you are doing is changing the description of the state, or you are measuring the temperature in Celsius, and then in Canada people talk about things in Celsius, temperature in Celsius. You cross the border, you came to the US, now you have to talk about Fahrenheit. What you've done is change the description of the state, but that doesn't mean that the input output characteristics of the system is going to change. Okay, and generally speaking, in so, impulse response is not very difficult. Like, for instance, I know all of you have made paper planes and you have thrown the paper plane. That's an impulse response of that particular system, that paper plane system. So when you throw it, the moment you throw it in the air, that's the impulse on that particular plane. And now, however the plane is landing, that's the impulse response. So you can measure the response, you can see how the plane is landing, and you've given it an impulse, and that's your ht comma tau. So 3D trajectory, that particular paper plane tracked is the impulse response. Okay. And because it's a paper plane, you're not quite powering it at every point of time. So all you're giving it is an impulse, and then you're looking at what the output is going to look like. Any other question? Okay. So changing the description of the state doesn't change the impulse response. And if you have changed the description of the state, your A matrix would change in this way, your B matrix would change in this way, your C matrix will change in this way, and the D matrix doesn't change. It remains the same. All of this material that I talked about is covered in section 3.4 of the book. Okay. So mathematically, the impulse is infinity at time t naught and then 0 everywhere else. In reality, typically the impulse signal would be either like a triangle at t naught, or it could be a square waveform, a very narrow waveform at time t naught. So this is your u of t. Okay. What else is an okay? So when you're driving on a highway, you press the accelerator and then you stop pressing the accelerator. That's an impulse response. Let's say you press the accelerator for 1 second or 2 seconds, and then you leave it. That's an impulse response, and then the response, that's the impulse input, and then the response, which is how the velocity of the vehicle changes over that post that response, is essentially the impulse response of the system. Okay, now we move to chapter 4, which is on stability. So if there are no further questions, I'll move to chapter 4 of the book. The notion of stability is one of the central themes in the controls area. Okay. So James Watt designed the first steam engine. That's what we have studied in our history books. Designed the first steam engine. Turns out that there were steam engines before it. But what James Watt created was an automatic controller for that steam engine. Why was that automatic controller important? It was called the governor back in 1760s, I think. That's when he created it. So the problem was that the steam engines were prone to blowing up. What does blow up mean in the language of control systems? It was unstable. And it was unstable for various reasons. So I think the problem that they were trying to solve was there is a given. So they wanted the state of the system, which is the pressure of the boiler or something, to be within a certain band. And if it is going outside that band, it means that things are becoming unstable, and sometimes that would lead to a disaster and loss of human lives. So being able to control it automatically was a very important topic. And then James Clerk Maxwell, the same guy who came up with Maxwell's equation, he did the first analysis of governors back in 1857 or 56, and that's considered the first paper in control systems. And why do we study control systems? Of course, we need to design controllers and so on, but the reason to design controllers is to make sure that the system becomes stable. So what is stable? What is stable? Stable systems. So I have a nonlinear system and x of t naught equal to x naught, and I'm going to make whatever assumptions is needed to have a unique solution. So you can have unique solution in the vicinity of x naught, you can have unique solutions closer to t naught, and so on, but just assume that there is a unique solution within certain bounds, and we are just focusing our attention on that particular region of the space where we have a unique solution to this differential equation. So definition, a point XE in Rn is an equilibrium point if and only if f of xe equals to 0. And this is a exercise that you have done earlier in assignment 1, which is to find the equilibrium of dynamical system. I know I have not put ut here, so just assume that ut is a function of xt for now. So we have like an overall description of the system that's just a function of xt. And we have an equilibrium point for that particular system. We'll talk about stability in a bit. But what's a desirable characteristic of a system? One desirable characteristic of the system is that no matter where you start from, you can get to the equilibrium in some time. That sometime could be 5 seconds, that sometimes could be 5 microseconds, and that sometimes could be 5 hours or 5 days. So we'll get to that definition in a bit. But the first thing that I want to do is a little bit of an abstraction. So I'm going to define a new state. W equals to x minus xe, then W dot equals to W dot of t f of W t plus xe and I'm going to call it capital F of Wt. And in this case, what's the equilibrium of this? What's We? What is We? What's the equilibrium of this system? At what point of time this capital F becomes 0? So if capital F is 0, that means that this term is 0. So Wt plus Xe equals to Xe, which means that Wt is equal to 0. So my equilibrium, the new equilibrium under the new state space becomes 0. So generally speaking, in controls, we always assume that the origin is stable because I can always translate the state and come up with a new dynamical equation of the system so that 0 is the stable point. Oh, sorry, I'm talking about 0 is the equilibrium point. We'll talk about stability in a bit. So there are different ways to talk about stability. So what is stability? Ideally, we want the state to get to the equilibrium point as soon as possible. So to give you an example, you've set your temperature within your cabin to be 72 degrees Fahrenheit, and you went to your friend's place and the friend opened the door and a lot of hot air came in. Now your cabin temperature increased to 74 degrees Fahrenheit. You close the door. Now you're going on a highway or you're going within the city. Ideally, you want the temperature to come back down to 72 degrees Fahrenheit, right? So then it's an equilibrium. Then you are, then you are getting to the equilibrium point within a reasonable amount of time. So this whole notion of stability was studied quite extensively by Lyapunov. And there are many definitions for studying the stability of the system. So the first, so food for thought for the first definition. The most, I would say, general definition for stability is Earth stable? So Earth is revolving around the sun. Should we consider Earth to be stable or not stable? So we have a periodic orbit. We have a state which is going in a periodic orbit. Is that stable or not stable? So this duster is stable. Okay, it's not moving. Right? This chalk is stable. This board is stable. Everything is stable inside the room, which means that it's static. It's at one place and it will remain at that place until a force is applied on it. But let's think about Earth as a whole, right? So it's revolving around the sun. Should we consider it as stable or unstable? What would instability mean? Okay, what are your thoughts? Yeah.
Well, I guess it would be depending on what state vectors you take. It could be stable or unstable, right?
Okay.
And then there's also, I guess, marginally stable, right? So if you look at just the x-y coordinate around the sun, that's periodic. But the radius and the speed around it don't change. So
right.
In that case, it would be stable.
It would be stable. Okay. Yeah. Okay. So that's one thought. So one option is to change the description of the state itself so that we can call it a stable state because it's going in like a unique orbit. I think that's a perfectly fine idea. Same?
I would say it is stable just because if you were to move the Earth, which would be very hard, it would still be moving in a
right.
circular orbit until a point very far away, in which case you're out of the sphere of influence of the sun.
No, but even if it goes out of the sphere of influence of sun, it becomes an unstable system. But because the state is going to infinity, I'm kind of assuming that you've seen some notion of instability and stability. But let's think about it. So Earth has been revolving around the sun for maybe like 4.5 billion years. I could be off by a few years, but that's roughly what people say. And it's been revolving around the sun for pretty much the same, with the same radius and the same sort of number of days it takes to revolve around the sun. So what should be a good notion of stability? So if we want to call it stable, because it's been doing the same thing for 4.5 billion years and it's probably going to do the same thing until the eternity, what exactly is a good way to define the stability of a system of this type? Yeah.
It can be described by some function which does not go to infinity.
Okay, that's a good start. Yeah. Okay, that's a good start. So it's not going to infinity in infinite amount of time, I guess, right? So that's a good notion of stability. But the way we can write it mathematically is as follows. So that's the first definition. Definition 4.6. X equal to 0 is stable. So it's an equilibrium. said to be stable if, I personally like to use if and only if in the definition because that's the definition. For every epsilon greater than 0, there exists delta epsilon greater than 0 such that phi of t x naught norm is less than epsilon for all t greater than equal to 0. So here t naught is equal to 0 as well whenever norm of x naught is less than delta epsilon. Okay, so what is it saying? If the trajectory is contained in an epsilon ball around the origin, this is the epsilon ball around the origin, or you can think of it as epsilon ball around the equilibrium point. So if in case your equilibrium point is not at the origin, it's at some point in the space, then you are within the entire trajectory for time t greater than equal to 0. So t goes from 0 to infinity. The entire trajectory lies within the epsilon ball whenever x naught, which is the initial state, it lies within delta epsilon ball. Now, I know that we talked about Earth, and Earth is kind of revolving around the sun in a circular pattern, but you could have elliptical pattern, like for instance, asteroids tend to circle the sun around, revolve around the sun in an elliptical orbit. And satellites are revolving around Earth. Some satellites are revolving around Earth in an elliptical orbit. So it takes care of all of those situations. You could also have some sort of orbits that are sort of wobbly in nature. So you have, this is your x naught, and you could have trajectory that looks something like this. This is your phi of t x naught, and this is your epsilon ball. So my entire trajectory is contained within the epsilon ball whenever x naught is within the delta epsilon ball of the equilibrium point. Okay, it doesn't have to go to 0, by the way. This doesn't have to go to 0. So I've drawn it like it's going to 0, but you could also have a situation like this. So in which case delta epsilon equals to epsilon. This is your x naught, and this is your phi t of x naught. So delta epsilon is equal to epsilon. So for every epsilon greater than 0, I can find a delta epsilon which is equal to epsilon, such that the entire trajectory is within the epsilon ball whenever x naught is within the epsilon ball. Or you could also have a situation where your trajectory looks something like this. This is your equilibrium xe, and you could have x naught right here. I'm not able to make a good circle, but this is my epsilon ball, and this is my delta epsilon. Okay, so all of these three trajectories that you are seeing on the board, they are stable according to this definition. So it's a fairly general definition. It's not saying that things have to go to origin, which is the equilibrium point. So we don't have to get to the equilibrium point. As long as we are in the vicinity of the equilibrium point, we are good. We are in a stable system domain. Or rather, the equilibrium is said to be a stable point. Okay. Now definition 4.7. Equilibrium x equals to 0 is said to be not exponentially, sorry, asymptotically. If and only if x equals to 0 is stable and two, there exists eta greater than 0 such that limit t goes to infinity p t x naught equals to 0 for all x whenever norm of x naught is less than eta. The set, let me call this D, x naught in Rn such that limit not equals to 0 is called the domain of attraction. Okay. So this notion of stability said that if you are in a periodic orbit, you are fine, you are stable. This notion of stability is saying that not only you are stable, but you are actually eventually converging to the stable point. Okay, so whenever you are starting close to the stable point, eventually you will converge to the stable point. Now you have a bunch of points from which you can converge to the stable point, You collect all of them together and you call it the domain of attraction. This is the domain of attraction of this particular stable point. So I built my air conditioning system in the vehicle in a way that if I set the temperature to be 72 degrees Fahrenheit, the 72 degrees Fahrenheit becomes the domain of attraction. So no matter what the temperature is inside the vehicle, on a hot summer day, the temperature inside the vehicle can go up to 100, 105 degrees Fahrenheit. So you parked your vehicle on Walmart parking lot, you went to do shopping, you came back, the temperature inside the cabin is 105 or 110 degrees Fahrenheit. You turn on the air conditioning system, the domain of attraction, if things are stable, if your system is working as intended, eventually you will converge to 75 degrees or 72 degrees Fahrenheit because that's your equilibrium point. And eventually, after some time, maybe 5 minutes, maybe 15 minutes, maybe 30 minutes, you will converge to 72 degrees Fahrenheit, and that's the domain of attraction. When would the domain of attraction, well, when would your temperature not converge to 72 degrees Fahrenheit? So you went inside your cabin and you turned on your air conditioning system and you see that the temperature is not falling down. Why would that be the case? Yes.
You need a better car.
Maybe you don't have the budget for a better car, but you might have a budget to buy something else from Walmart to fix the car. What could that be? Yeah.
Well, I was gonna say, look, I guess it would be obvious if you had it set not to 72, that would never convert to 72.
That could be the case.
But,
yeah.
I guess if you were out of refrigerant or something.
That's right. So some refrigerant leaks from the vehicle for whatever reason. It could be because the vehicle is old or whatever. So you just need to recharge the refrigerant, and then again 72 Fahrenheit would become the domain of attraction. So the domain of attraction is for this specific system, which has a very specific refrigerant level, which has a very specific blower setting and so on. But as soon as you change the setting or the refrigerant has leaked or whatever, and now you don't have enough pressure, then the function f would change, in which case the domain of, the equilibrium point will change. So maybe you cannot reach the 72 degrees Fahrenheit setting, but you can reach 80 degrees Fahrenheit setting because that's the amount of refrigerant you have left in your vehicle. That's what the stable equilibrium is. So your system is stable, but eventually you should converge to the stable point whenever you are starting close to the stable point. Okay, so eta could be any positive number. Not any, but there exists a positive number such that if you start sufficiently close, you converge to the you converge to the stable point. How many of you have taken optimization class 5500? No? No, okay, only one. Okay, so in optimization, whenever you are training neural network or whenever you are doing some sort of training of machine learning models, typically the stable point, the equilibrium point is your trained values, whatever the trained values are. That's the final model, that's your equilibrium point. And then you want to design an algorithm which is not just stable, but it's asymptotically stable, which means that you design your algorithm, which is f, in a way that eventually you converge to the equilibrium point in your during your optimization process. So whether you're doing reinforcement learning, whether you're doing machine learning, whether you are training a model, whether you're doing optimization, f is the algorithm that you have, and equilibrium point is the eventual point that you want to converge to, the optimal solution that you want to converge to. And so you design your algorithm f in a way that the desirable point is your equilibrium point, and your algorithm is asymptotically stable, which means that you converge to that equilibrium point as t goes to infinity. So if you train for infinite amount of time, you will converge to the optimal solution. Those of you who have taken the optimization class or any of those reinforcement learning classes, you would have seen that behavior whenever you are running the optimization algorithm. Okay, so this is asymptotically stable system. What that means is eventually, as t goes to infinity, you converge to the equilibrium point. Now let's talk about exponentially stable. Okay, so given this figure, not asymptotically stable, not asymptotically stable, asymptotically stable, okay, because it's converging to the equilibrium point. So Earth is not asymptotically stable, but it is stable. Let's talk about exponentially stable. I hope I should. I'm going to define exponentially stable if and only if there exists alpha greater than 0 such that for every epsilon greater than 0 there exists delta epsilon greater than 0 such that there is a error in the book. There should be a negative sign here. So keep that in mind. This is definition 4.8. The error in the definition is that the book doesn't put a negative sign here, but there should be a negative sign here in the exponent, e raised to minus alpha t. Multiplied by epsilon. Okay, exponentially stable is further, it's much stronger. So stable means it can be a periodic orbit, that's okay. Asymptotically stable means as t goes to infinity, it should converge to the stable equilibrium. Exponentially stable means that now you are forcing the speed of getting to the equilibrium point to be exponential. Okay, so this one is decaying, this one is getting closer and closer to the equilibrium point exponentially fast. And this is the gold standard. Being exponentially stable is the gold standard. We always want to be exponentially stable. But it's extremely difficult in many situations. I mean, I think we definitely aspire to be exponentially stable, and in most cases you can design systems that are exponentially stable, but you could have a situation where things are not exponentially stable and you can't really help it. I'm not able to think of an example that is asymptotically stable but not exponentially stable, but I'm sure if you do a quick search on Google, you will be able to find something. So generally speaking, in exponentially stable system, you will see that it's converging to the equilibrium exponentially fast. So those of you who have taken an optimization class, most of the algorithms that we talked about in optimization class are exponentially stable algorithms, and so it converges to the optimal solution, which is the equilibrium point of that algorithm. It converges to that equilibrium point exponentially fast. If you're flying at 30,000 feet and a wind gust comes, the flights are designed to be exponentially stable, so it might go to 30,100 feet, but then it will eventually converge to 30,000 feet very quickly, even despite having that gust. So whenever you start close to the equilibrium point, the entire trajectory gets close to the equilibrium point exponentially fast. With this is the amplitude and this is the exponential term that determines how quickly it's going to the stable point. Any questions so far? So those are the three notions of stability: stable, periodic is okay, this kind of orbit is okay, this kind of orbit is okay. So it's much more general. Asymptotically stable, this is okay, but these two are not okay. These two are not asymptotically stable. And exponentially stable means now your decay or your trajectory has to converge to the equilibrium exponentially fast. In this case also, you can define the domain of attraction for the exponentially stable equilibrium, and so you will have a domain, and if you start within the domain, you converge to the equilibrium point exponentially fast. And then there is a definition of globally exponentially stable, which means that the domain of attraction is entire Rn. So no matter where in the state space you start with, you will converge to the equilibrium exponentially fast. And then globally asymptotically stable is no matter where you start in the state space, you will converge to the equilibrium point as t goes to infinity. Now, what is the definition for instability? Definition 4.9, an equilibrium x equals to 0 is unstable if and only if it is not stable. In this case, there exists epsilon greater than 0 and a sequence xm going to 0 and Tm such that So if you have an unstable system, no matter how close to the the equilibrium point you start, you will have a situation where the trajectory is going to be outside of the epsilon ball, no matter how close to the stable point you start. So I'm standing on a mountain. I'm standing on Mount Everest. I'm standing right here. I'm at an unstable equilibrium. Okay, because I don't have any special climbing skill. So if I move away from here, this is the trajectory I'm going to take. Okay, so I'm going to be outside the epsilon, no matter how. Like if I'm standing at the top, I'm fine. But if I just move like 1 millimeter away from the top, my trajectory is going to be outside of the epsilon ball after some point of time. Okay, and in my case, probably there'll be like few seconds. After a few seconds, I'll be like outside of the epsilon ball. This is the epsilon ball. Okay, so that's an unstable equilibrium. You have a battery pack, and I don't know, the thermal management system of the battery or the BMS of the battery is not functioning as intended. It's a very hot day in downtown Los Angeles. And it turns out that there are some exothermic reactions within the battery. And no matter how close to the equilibrium point you are, because of the situation around that battery, eventually there will be a thermal runoff, as a result of which the battery is going to blow up. That's the case of an unstable equilibrium. So your battery is at an unstable equilibrium. How do you get to a stable equilibrium? Well, you write a better software, you create a better battery management system, you isolate the battery packs or the cells appropriately, you put enough number of temperature sensors around the battery to be able to better observe the battery and make sure that the temperature of the battery doesn't go beyond a certain level. Yes, please.
So when you're controlling a system like that, are you changing T or are you adding to the left-hand side such that?
Very good question. When you are updating the control strategy, what you are doing is changing the F itself. So you may not change the equilibrium point. You may not change the equilibrium point, but you are changing the stability of the equilibrium point by a better control strategy. And many a times, when you are changing this, you need to have some source of energy to be able to do that. So in the case of battery pack, that energy comes from the battery itself, right? So always remember that some of these conservation laws will kick into action whenever you do that. So you might have to have a better battery pack, better power electronics, better this and better that in order to be able to serve and make that system exponentially stable. Yeah.
If you have a system with no points of equilibrium, but you do have active control, can you make it stable? Or
yes, rockets are a good example of that. So in general case, the rocket is supposed to just fall on the ground. Like it can't even be standing straight because a wind gust will come and it will make it unstable and it will fall on the ground. But the whole point of adding all the thrusters and control surfaces on the rocket and pitot tubes and whatnot to measure the airflow is to make sure that the F is stable. Or, well, what's the stable point of a rocket? Well, it goes in the orbit and then it just remains within the orbit. So that's probably the stable point. It's the stable equilibrium, but it's not exponentially stable and it's not asymptotically stable. It is just stable because it goes in the orbit and then it remains within that orbit, the satellite. Okay. So we studied quite a few notions of stability and unstable systems today. In the next class, we are going to continue to talk about Lyapunov stability for the linear system, and we'll characterize under what conditions are linear systems going to be stable. That's the topic for the subsequent class. I have not prepared more material beyond this. I thought it will take the entire class, but incidentally, I have 10 minutes left. So important announcements. Next Thursday, there is no class. because of some personal commitment. And homework 2 is up. So I have given you a few examples from aerodynamics to find modes, certain modes of aerodynamic systems like an aircraft. So hopefully you will have fun doing the assignment. And for question number 2 and 3, you are allowed to use generative AI tools like ChatGPT or Gemini or whatever to be able to write the code to solve that particular problem. So that's all for today. Thank you so much, and I'll see you next week on Tuesday.